Municipalities and local businesses are rapidly transitioning to localized mesh networks. In a mesh network, infrastructure nodes connect directly and dynamically to one another to keep local digital economies online. But this decentralized approach exposes a severe security gap. Local governments lack the budget to staff a Security Operations Center, or SOC, with human analysts monitoring the network 24 hours a day. Because municipal networks operate continuously, they are constantly targeted by automated ransomware probes and cyber attacks. These strikes overwhelmingly occur during off-hours, when local IT closets sit completely empty. Large enterprise networks handle this volume of threats by deploying massive, highly paid security teams to monitor traffic around the clock. Without that dedicated human oversight, a town's digital infrastructure is left entirely defenseless during its most vulnerable hours. The standard solution for small towns is to outsource their security to remote cloud providers like AWS or Microsoft. Relying on external cloud security introduces three critical flaws. It creates WAN latency by forcing local traffic to travel over wide area networks, violates data privacy by exporting municipal logs, and introduces a single point of failure if the local macrogrid loses connection to the outside world. True resilience requires an air-gapped infrastructure bundle that operates autonomously and entirely within the local perimeter. This is the architectural purpose of the Digital Nervous System Core Bundle, designated as SKU-SOV-BNDL-DNS. This system places a localized large language model, functioning as an autonomous DevOps sovereign, directly at the physical and logical center of the town's network. A large language model, or LLM, is an AI system trained on massive amounts of data to understand and generate human-like text or code. The deployment begins inside a secure municipal data center or local ISP facility, starting with a standard blank 19-inch IT rack. Technicians install the core compute layer by slotting three 1U high-capacity Sentry Pro Edge servers into the rack. Each individual node is powered by an Intel x86-64 architecture, paired with 64 GB of RAM and 4 TB of NVMe storage configured in a RAID 1 array. NVMe is a high-speed data storage protocol, and RAID 1 mirrors that data across multiple drives to prevent data loss. These extreme hardware specifications are not designed for standard file storage. They provide the necessary bandwidth for distributed LLM inference and massive continuous log ingestion. To handle that throughput, a 16-port 10 gigabit managed municipal backbone switch is added to the rack. Thick, shielded DAC cables physically link the switch to the three compute nodes. DAC, or direct attach copper, is a high-speed, shielded cable designed for zero-latency interconnects. This switch serves as the central funnel, aggregating all server and network log traffic from the entire town and directing it into the compute cluster. Together, this physical setup provides the raw compute density required for an autonomous AI to operate continuously at the edge of the network. With the physical layer established, the system requires an operating system to manage the hardware. The servers are flashed with the RIOS Core Clustering OS, which is built on a Proxmox and Ubuntu foundation. This software enables a high availability, or HA, architecture. The three separate physical servers logically link their individual resource pools to form a single active-active swarm. This structure addresses a primary physical threat, risk HW03, a catastrophic power supply failure that destroys one of the physical Sentry Pro nodes. If a node dies, the mitigation protocol executes immediately. The LLM and DevOps containers instantly migrate away from the failed hardware and restart on the two surviving servers. Because the compute load shifts instantaneously, this container migration happens with absolute zero downtime for the system. In a traditional single-server setup, a hardware failure requires a human technician to manually replace parts and restore backups, resulting in hours of critical network vulnerability. By distributing the load, the active-active swarm architecture renders the physical cluster practically unkillable from a local hardware failure perspective. Next, the cluster must establish a secure identity on an untrusted network through a specialized provisioning workflow. The initialization process requires a unique cryptographic SHA-256 hash. SHA-256 is a cryptographic algorithm that produces a fixed-size, unique mathematical signature to secure data, which unlocks the enterprise multi-node container orchestration. Once unlocked, the system establishes the Root Certificate Authority, or Root CA, for the municipal mesh. A root CA is an entity that issues and verifies digital certificates to authenticate identities on a network. This establishes the cluster as the absolute root of trust. It becomes solely responsible for issuing and revoking digital certificates for all connected infrastructure, like the local Main Street nodes, accepting only internal commands. Because this operates as a closed cryptographic loop, it guarantees absolute data sovereignty. Network data is never transmitted to external APIs like OpenAI or AWS. With the network secured, the cluster spins up its final software layer, the OpenClaw Deep Admin image. This software deploys an Ollama swarm running a localized Llama 3 8B model, fully awakening the autonomous AI sysadmin. Once online, the system begins massive log aggregation across the town's intranet. A built-in pipeline called the Sentinel aggregator continuously ingests firewall and server logs from every connected local business and utility node. The Deep Admin AI parses millions of these log lines in real time. It uses semantic understanding to differentiate harmless network noise from coordinated threats, like an SSH brute force attack. SSH, or Secure Shell, is a network protocol that provides a secure way to access a computer over an unsecured network. Consider a targeted ransomware probe. When an external actor attempts to exploit a local municipal clinic's database, the resulting alert log routes immediately to the central AI. The Deep Admin responds instantly. It communicates with the local municipal switch and executes a no route command, dropping a blockade that completely shields the town from the attacker's IP address. The system also manages internal stability. If a local library node crashes due to a standard memory leak, the cluster detects the failure. Recognizing the dropped heartbeat signal, the Deep Admin initiates a secure SSH connection back to the failing hardware via the mesh network. It runs automated diagnostic checks and restarts the failing systemd service over the local mesh. Systemd is a core software suite that manages system services and processes in Linux operating systems. These automated repair and defense protocols ensure that human IT directors do not have to be woken up at 3 a.m. to handle routine crashes or perimeter probes. Operating an AI entirely at the edge introduces logistical risks, specifically risk OOM02, known as log exhaustion. During a DDoS attack, an influx of connection logs could rapidly fill the 4-terabyte NVMe drives, leading to a total cluster failure. A DDoS, or distributed denial of service attack, disrupts normal traffic by overwhelming the target with a flood of malicious internet requests. To prevent this, the Deep Admin constantly monitors its own storage capacity. If drive usage exceeds 85%, it aggressively compresses cold logs and deletes the oldest non-critical data. There is also risk SEC01, the danger that the AI might misinterpret a legitimate surge in local traffic, like a voter registration deadline, as a DDoS attack. The system relies on a human-in-the-loop failsafe to mitigate this. While external threats are blocked instantly, banning internal mesh IP addresses triggers a manual yes or no override prompt sent directly to the IT director's Signal app. When fully deployed, this core bundle operates as the central intelligence of the municipal mesh. Combining high-capacity local hardware with distributed LLM inference turns a passive town intranet into an active, self-healing entity. Threat detection and vulnerability patching are handled locally. The network no longer relies on remote human SOC teams or fragile macrogrid internet connections. For local economies to survive modern cyber threats, absolute data sovereignty and autonomous edge compute are no longer optional. They are the required foundation for secure municipal infrastructure.